Hey class, in this video, just wanted to go through the example here for how to perform that goodness of fit test and kind of using Excel to help us do this a bit quicker, right? So in this question, we have a retail trade association. They claim that the tax preparation method for adults are distributed as follows, right? So they're saying these percentages are true. 24% of adults use an accountant, 20% do it by hand, 35% use computer software, 6% have a friend or family, and then 15% have a tax preparation service, right? So a tax company randomly selects 300 adults and asks them how to prepare their taxes, kind of going by these methods, right? And they get these results from their sample, right? At the alpha equals 0.01 level of significance, test the association's claim, right? So the association saying these percentages are true. This tax company is going to use this sample to look and see if it lines up with these percentages that were given, right? So first, let's kind of describe, okay, thanks for that. Star Wars and Fortnite. Let's describe what the null hypothesis and alternative hypothesis is going to be, right? So the null hypothesis in these types of problems is always going to be, we're going to assume the percentages are true. So we're going to assume the frequencies given are true. You can write this a bit more long-windedly, right? Assume that the percentage of adults who use an accountant is 24, by hand 20, right? You could do it and write it out that way, but I'm just going to represent it as assume all these frequencies are true. And my alternative is the opposite, right? The frequencies are not true, right? Not equal to those values that are given, right? We're going to perform this test to see if we have enough evidence to say that these given frequencies are not the true frequencies, right? So to do this, Excel is your best friend for this stuff, right? What do we have? We got to find our expected frequencies. And we're also going to find our observed frequencies. Observed frequencies are just what we have from the sample, right? Maybe I should label this a bit more. Let's move this over. Let's just detail the methods here. So methods, we have accountant, by hand, computer software, friend, family, and tax prep service. All right. Observed frequencies are just what we have from the sample, right? So they're just the frequencies we have from our sample. So that's going to be the 63, 40, 115, 26, 53. Okay. The expected frequencies are, remember, we can find this by taking our sample size and multiplying by these percentages here, right? So it's going to be n times pi, where pi are those different frequencies. Let me plug in my laptop here. Okay, so I'm going to be taking my sample size, which is 300, and multiplying it by the percentages that I'm given for each category. So I'm going to do 0.24. I'm going to do 300 times 0.20, 300 times 0.35. So in each of these cases, it's just sample size, 300 times these expected percentages right here. What were we on? Friend and family, 0.06, then 300 times 0.15. Cool. So these are, if these frequencies were true, this is how many people in each category we would expect to see if the frequencies are true, right? And if we look at our sample, of course, it's a random sample. It's not always going to perfectly align with this. But 72, 63, a bit of a difference there. 60 and 40, there's a bigger difference there. But some of these are a bit closer, right? And that's going to happen in a random sample. From here, it is just a matter of finding the test statistic, right? So these are my expected frequencies, also known as the E. These are my observed frequencies. These are the O in terms of that equation, right? Let's make this a bit, why did I get a weird E there? Cool. So what I need to find in this column here is that equation. We do E minus O squared, and that's divided by E. So what I'm going to do is write out this equation for each line, right? So I'm going to write out my expected frequencies, and let's do this in parentheses. Expected frequency minus my observed frequency. I want to square that. And then I'm going to divide again by my expected frequency. Okay, that's what the equation for the test statistic is doing, right? It's E minus O squared over your expected frequencies, right? And I want to do this for each of these categories, for the accountant category, for the by hand, for computer software, friend and family, and so on, right? But if you're doing it by hand, you can totally do it just piece by piece, then add everything together, right? Nice thing about Excel is because I referenced all of this correctly, right? I'm doing blue minus red squared divided by blue. It will repeat that same type of process for the next line, right? It's just taking blue minus red squared divided by blue again, right? So very quick, just by clicking that bottom right part of the box there, just click and drag and you'll get all your values there. Now the test statistic is the sum of all these values. So my test statistic right here, let's make that arrow a bit longer, is going to be the sum of all these observed differences, right? So I'm gonna just use sum, yeah, equal sum, choose all those values, and you'll get your test statistic right there. All right, so that's our test statistic for this hypothesis, right? I also need to compare it to a critical value. For this hypothesis. Then I can figure out, am I going to reject or fail to reject the null hypothesis, right? So for my critical value, this type of test is really nice because I don't have to worry about left-tailed, right-tailed, two-tailed, that type of thing. It's always going to be the same command here. So it's going to be chi-square.inverse, and we can put .rt for right-tail. And all you have to put in here is your alpha. So let me check what that was. 0.01, cool. 0.01, and degrees of freedom. So degrees of freedom is a bit different here. So it's not the usual sample size -1. It's not going to be 300 minus 1, right? In this case, degrees of freedom is based off the number of categories. So in this case, we have 1, 2, 3, 4, 5 different categories, and we're going to use that to find our degrees of freedom. So we're going to do 5 categories minus 1, which is 4, but if you type it out, that's fine as well. And that should give us the critical value. All right. Okay. Pretty close to each other. All right. Okay, so we have our test statistic, we have our critical value. Now it's just a matter of figuring out, do I reject or fail to reject? Let me try to do this in Paint. Excuse my awful drawings again, but, or last time I was writing something. All right, so chi-square distribution, let's redo that, is a skewed right distribution. So you got a little bit of a right-tailed here. Doesn't matter exactly what it looks like, and we have a right-tailed test, so we have some critical value here where the area to the right we are shading off as our rejection region. That looks like something. All right. And it's the same situation for every goodness of fit test, right? So the critical value that we found was 13.27. Can I type? So that is where this rejection region starts at 13.27. And our test statistic, let's just do this in blue, is actually to the right of this. So 13.27 is this kind of threshold, and then we get something barely to the right. What did that end up being? 13.72. Okay, so because our test statistic is in the rejection region, we are going to reject the null hypothesis, right? Sorry about this awful picture here, but like it's going to be the same picture every time, right? You're always looking in the right tail. The critical value is where the rejection region starts. And then if your test statistic is in the shaded area, reject. If it is somewhere over here to the left, right? So if I got something like 8.4 and it was like something right there, I would fail to reject, right? Yeah, when I'm using critical values, it helps to just draw a picture just to know kind of what I'm looking for. So let's finish this up. So I am rejecting, right? I'm in the shaded area, so I reject. I can reject this claim, and then kind of state, kind of going back to my problem, I can state that there is significant evidence to say that the frequencies given from the Retail Trade Association are not accurate, right? So these frequencies that they gave me are not accurate, right? It's kind of a weird test because I'm not making any sort of conclusion about which ones aren't accurate, right? I can kind of tell from my sample that maybe by hand is a bit different than what is estimated. Maybe friend or family as well, but not generally good practice to kind of make those conclusions. You can kind of go on to perform a different type of hypothesis test kind of narrow down which ones are different. This one is just, this test is just kind of comparing these two claims, right? Assume these percentages are true versus the alternative. There is some sort of difference. I'm not saying which one's wrong. They could all be wrong, or maybe one of them is wrong, but there is some sort of difference, right? And that's kind of what the goodness of fit test can be used to do, right? For categorical data. It can be extended to a bunch of different other situations, but this is just one of those situations. All right, well, I hope this video kind of helped. Yeah, if you have any questions on this section, feel free to let me know. And yeah, I'll see you guys.